Yeah, I'm going to explain 2D simulation of supersonic flow through a CD nozzle. So I'm going to take this kind of domain for the computational analysis. So I'm not only taking the CD nozzle, I am taking the additional flow domain so that I can simulate the exhaust jet properties also behind the CD nozzle. So I am taking pressure inlet for this line, then this is the CD nozzle wall, then the bottom one will be the axis symmetric because I am going to take the rocket engine nozzle which is having the circular cross section. So if you make this as a half model, then it will be like this. So as it is a circular cross section, I should give it this as a axis. Instead, if it is like a CD nozzle used in the wind tunnel, then it will have a square cross section. So within that there will be a CD nozzle. So this, if you want to convert this into a 2D, then that will be a planar. Then if it is a planar, I have to give the symmetry. Okay, so this is the axis symmetric model. So I am giving axis for the bottom line if it is circular cross section. Instead, if it is a square cross section like a CD nozzle used in the wind tunnel, then this is if you cut into a sheet, it will be like a planar. Then we have to define the symmetry. So this is how it will vary. So here I am going for the axis. Then there is a pressure outlet. Then these two lines, now I am going to take it as a wall. Sometimes we can take this as a pressure far field also. That is, whichever the static pressure we are defining here, same thing we have to define. Same thing, that is pressure and temperature you have to define. But for simplicity, I am taking the wall because I have taken the enough distance here. So I am going to take this as a wall to simplify the simulation. Then to get the supersonic flow through this CD nozzle, two parameters we have to vary. One is the pressure difference between the inlet and outlet. Another one is the proper area ratio. Okay, so using the isentropic relation, I am going to find what is the inlet area, exit area, throat area. Then to introduce this pressure difference, there are again two methods. Like one is the blow down type. So here you can take the high pressure and it is open to the atmospheric condition, low pressure. So here for example 1 atm, high pressure assume we have 10 atm, and due to the pressure difference, that's around 10 atm pressure difference we have. Due to that, in the CD nozzle we are getting the subsonic to sonic, sonic to supersonic Mach number we are getting. This is the one way. So this way if you are simulating, then the exit pressure will be atmospheric condition only. So we may not change the operating condition. Simply we will use 0 Pascal for the pressure outlet. Then another method is like a suction type. That is, air is sucked from the atmospheric condition. So here 1 atm, then it goes through the, at the end we have the vacuum chamber. Then here we should have the very minimum pressure. For example, same 10 atm pressure difference if you want to produce, then here it should be 1 atm, so that the pressure difference will be a 10 atm to get the supersonic flow at the exit of the nozzle. So if you are going for the second type, suction type, with the low pressure region and the exit, then I have to change the operating condition to 0. Okay, I should not keep this 101325. I have to change this operating condition to 0 Pascal. Then in the pressure outlet, I have to give the required pressure. It may be some 2000, 3000, 5000, depends upon the exit Mach number, whichever it is that I have to enter. Okay, so if it is a blow down type where the flow is leaving to the atmosphere, no need to change the operating condition and no need to change the pressure outlet. We will leave it with the 0 Pascal. If it is like a suction type, then operating condition should be 0, and then the low pressure value you have to enter for the gauge pressure. So these two way we have to introduce the pressure difference. So I will go for this, the bottom method, suction type with low pressure at the exit. So as I am taking suction type, so in the front I have atmospheric properties. So P0 101325 Pascal, T0 300 Kelvin I am taking. Then I am going to design the CD nozzle for the exit Mach number of 3. This is my second assumption. Then at the end we have the low pressure region. So using isentropic calculation, I am going to find what is the static pressure, temperature in the inlet and outlet of the CD nozzle that I have to find. So other assumptions what I am taking, so already I mentioned I am going to design this for the exit Mach number of 3, and other assumption, so I am going to take the exit area and the inlet area is same and it is 1 meter square, like that I am going to assume just to design the nozzle. So inlet area, outlet area I fixed. Then either you have to fix this length or you have to give the convergent divergent angle. Okay, this angle you have to give. So any one way you can fix this nozzle design. So you may take 15 degree here, 15 degree here, like that, or you can take the nozzle length. So in this simulation I have fixed the nozzle length. I think I have taken 2 meter. Okay, so I have fixed the P0 T0 stagnation pressure temperature as the flow is isentropic. P0 T0 will be constant throughout the duct. Then exit Mach number I fixed, inlet exit area I fixed, then length of the nozzle I fixed. So with that I can design the CD nozzle. Again, if I am going for planar type like CD nozzle used in the wind tunnel, then which will have the square cross section. So I assumed the area is 1 meter square, and in that case 1 meter height, 1 meter depth. So if it is 2D, then I have to take CD nozzle with 1 meter height. If I am taking only the half of the model, then I will take height is around 0.5 meter. Okay, if it is a planar type simulation, then the height will be 0.5 meter on both sides, and the bottom, this axis I have to take it as a symmetry as it is a planar. So instead of this planar kind of object, if I am going for the axis symmetric CD nozzle used in the rocket engine, then the cross section is circular. So area I assumed as 1 meter square. So circular cross section is pi r squared. From that I can find the r, which is 0.56. So the radius I got 0.56. So the height of this exit will be 0.56 meter as it is axis symmetric. So this is not a planar, this is axis symmetric case. So I have to define this as an axis. So in the previous case it is a planar, so I have defined a symmetry. Here it is axis symmetric, so I have to define as an axis. These two are very important. So I will go with this axis symmetry. So I will take inlet and exit nozzle height as the 0.56 meter. The next we are going to find the other parameters. So as I mentioned, P0 T0 already we defined, which is constant throughout the nozzle. Then area also we defined, we assumed. Then we are designing this for the exit Mach number of 3. That once you know the Mach number, using the isentropic relations, you can find the other properties like A by A star, P by P0, T by T0, everything we can find it. So A I already assumed, with that I can find the A star. From the A star I can find what is the R star. So already this R and all we fixed, it is 0.56 meter here, here also 0.56 meter. Then from this area I can find what is the radius in the throat also, like that. All three height we can find. Then from the P by P0, T by T0 ratio, so already we assumed the P0 T0 value. From that I can find what is the static pressure and temperature at the exit. So static pressure at the exit for the Mach number 3 is 2758.07. This one we will enter in the pressure outlet case. So once we finish the outlet conditions, we will go for the inlet conditions. You see in the inlet also area we assumed 1 meter square, and A star value also we found. Once we know these two area, we can find the area ratio. Then from the isentropic table we can find what is the corresponding Mach number, P by P0, T by T0. So as P0 T0 is already assumed and it is constant, I can find what is the static pressure and temperature. Like that I got all the static pressure in the inlet outlet, then P0 T0, Mach number, area, everything we found. With that we can go for the simulation. So for the simulation domain, we can take the complete domain, or we can take only the half of the domain. So in the half of the domain also, sometime they will extend this the flow domain up to the inlet, or sometime say this is the nozzle, this is the nozzle, at the end only they will add, like that. The domain will vary, depends upon their application. So I will take this bottom one. At the end of the nozzle I am going to add another one flow domain just to check the jet properties. So already I mentioned as I am taking the axis symmetrical nozzle. So inlet and exit nozzle height will be 0.564 meter, and from the calculation I got throat height will be 0.32 meter, and length I assumed into 2 meter, and it was sharp only. Just to give it a smooth flow in the throat section, I have given some radius here. Okay, so this is the CD nozzle. Then in that I have added the another one flow domain. So almost here I have taken more than 10 times the CD nozzle length along the length. Then in the vertically I have taken around 5 times the nozzle length. Okay, so in the horizontally I have taken more than 10 times the CD nozzle length. Vertically I have taken 5 times the length. Like that I have defined the flow domain. Then in the CATIA, using fill option, I created the surface. Then using the split option, I have divided this into 3 blocks. Okay, with the blocking I have finished. Then this file, already mentioned, I have given the naming like this is pressure inlet. These 2 walls will be the pressure outlet, and the bottom line is the access, and this is the CD nozzle wall, and these 2 also wall I am going to take as I have taken enough height. So this is the boundary condition I am going to use. Then this how I have measured it. Okay, so I have taken some coarse mesh only just for the demo purpose. So I have refined the meshes near the nozzle. So outside it was somewhat coarse mesh, and along the nozzle, see most of the flow changes occurs in this throat section. So we have to go for the refined meshes near the throat. Actually we can give fully refined meshes from the throat to the exit. Okay, so like that you can give. And normally for the proper research kind of work etc and all, you should go for the multiple blocking, because this is a single block. So if I keep on refine this mesh element here in the vertical line, what will happen? As it is compressed in this region, so these elements are skewed, stretched, okay, and deformed. So during the simulation we are getting the divergence error. You will get the divergence error. So to avoid that, you should go for the multiple blocking, so that you can refine the cells properly in this region. Okay, but for the simplicity here there is no blocking, it is a single block. So I am going for the just a coarse mesh, very less number of divisions only I have taken to avoid that divergence error. So this is how I have taken the mesh. Then, so as I mentioned, boundary conditions and all I have fixed. What is the area, Mach number, everything I fixed. Then I am going to run this simulation for 3 different conditions. One is the perfectly expanded. So already we found that value 2758.07 Pascal. So we will get the exhaust jet without any shock. There is no shock. Then over expanded, that is higher pressure, so that there will be an oblique shock formation. So the jet is converged, like that you will get it. Then under expanded, so very low pressure I am going to take. So there is a expansion fan, so the jet will be diverged. So these 3 we are going to see. And again another one catch is there. So what happened, we have taken just a simplified version of the CD nozzle, just 2 line only I have drawn. So at the exit the flow is not aligned with the free stream condition. Okay, due to this divergence there may be a small expansion fan formed for the perfectly expanded case. Okay, because original nozzle we will use the contoured nozzle, where the exhaust flow will be aligned with the free stream, like it is horizontal. It won't be like a diverged like the simplified version we have taken. So it should be the proper contoured nozzle using method of characteristics. But just for the simulation I have taken the like a divergent one. So in the perfectly expanded case I may not get this kind of parallel lines, because my nozzle is like that. Okay, so I won't get the parallel line like this horizontal line. There will be a small expansion will be there in the results. Okay, so instead of that straight line, if I take the contoured nozzle and with the exit aligned with this flow direction, then I may get this kind of parallel jet without any shock. only that it will differ. Okay, so with that we will go for the simulation. So I have finished both importing that file in the CATIA, and I finished the mesh generation also. Now you will straight away start with this ANSYS Fluent. So as this is a supersonic flow, I have taken the density based, because there will be a change in density, compressible flow. Then I left with the steady flow, because there is no much flow separation like a flow, the aerofoil, etc. and all. So I left it with the steady flow. And in this 2D space, as I am taking the axis symmetric rocket engine CD nozzle, I have changed it to axis symmetrical. Okay, by default it will be planar, but I am going for the axis symmetric, because I have taken height is 0.564, which is for the axis symmetric. If I am taking the planar, then I have to design the CD nozzle with a 0.5, like a CD nozzle used in the wind tunnel. So here I am going for the axis symmetric, as it is the CD nozzle used in the rocket engine with a circular cross section. So that's it about the general. Then in the model, so energy we have to on, because once it is density based, then there will be a change in density, pressure, temperature, everything will happen. So energy have to be on. Then in the viscous model, by default it will be a k omega SST in the ANSYS, but I am not checking what is the boundary layer growth, etc. near the CD nozzle wall. My aim is to get the just to check the flow inside the nozzle, also the exhaust jet. Okay, so my objective is not to check with the wall boundary layer growth and all. So just to simplify the simulation, I am going for the inviscid. Okay, so if you want to see the wall effect, etc. and all, you can go for some other model. So mine is just to study the flow property. So I am going for the inviscid, so that I can save the computational time. So energy on, that is must. Viscous I have taken inviscid. Then in the material, in the air, so the density, the default one will be constant, that we have to change it to ideal gas, so that using the ideal gas law, P is equal to rho RT, it will find the other pressure, temperature, density relations, everything. Okay, so for compressible flow, you have to change this density to ideal gas. So material I have changed. Then the boundary conditions. So first axis, by default it may be wall or symmetry. You change this to axis, first one. Then there is a CD nozzle wall. So this is by default wall, it is taken, so no need to change. Then inlet. So inlet, I am going to change this into a pressure inlet. So edit. In the pressure inlet, you see I have given the total pressure as 101325, like we already assumed. Then the gauge pressure, static pressure also already we found from the calculation, that is 999.38. Okay, 999.77.38 Pascal. So this static pressure I entered. Then stagnation temperature also assumed as 300 Kelvin. So all three I entered. Okay, stagnation pressure, and below that static pressure, then stagnation temperature. Additionally, there is an option called prevent reverse flow. See, as we have this much sharp domain, definitely there will be some reverse flow. So if you enable it, so system will prevent those reverse flow, etc. and all. So with the shortest iteration, solution can be converged. So if it is not enabled also, you will get the same result, but system will run for little more iterations. Okay, so to simplify the iteration, so I enabled this prevent reverse flow. So apply. Then pressure far field, that is these two walls I am taking as a wall only. Okay, so this is the CD nozzle. Okay, CD nozzle wall, and these two line as the wall I have taken. So sometime you can take it as a pressure far field also, but here to simplify I have taken as a wall. So then pressure outlet, if you see, so I defined the static pressure 2758.07 Pascal, whichever we got, 2758, that value I entered. And what happened here also, if it is not enabled, then you have to enter the temperature. stagnation temperature 300, and once if you enable this prevent reverse flow, other things are disabled. Okay, so if you enable this prevent reverse flow, then the pressure outlet, just this gauge pressure 2758 only you have to enter. Then important thing, this operating condition, by default the value will be 101325. You change that to 0. Otherwise, if you don't change this operating condition, the pressure outlet conditions whichever you are entered 2758 plus 101325, like that it will be taken. Okay, so to account this low pressure, you have to change this to 0. Don't forget, operating condition should be 0. So pressure outlet is 2758 for our case. So I defined everything. Okay, so at the bottom is access, and the CD nozzle and the top walls and all just to wall. In the pressure inlet, I have defined the stagnation static pressure. Pressure outlet, I have defined the static pressure. Like that, everything completed. Then reference value, I am initiating from the inlet condition. So approximately it is telling 47 meter per second is the inlet velocity. Then in the method, I am enabling all these 4 options because I am taking very coarse mesh. Normally for the supersonic flow with the shock capture and all, we should go for the very fine mesh, but just for the demo I have taken the very coarse mesh. So I am enabling all these things. You can see the convergence acceleration for the stretched meshes, because we have very coarse mesh, right? So there are a lot of stretched meshes, and there will be a lot of skewed meshes, etc. and all. So these options will accelerate the convergence. With a shorter time, the solution will be converged. So I enabled all these 4. Without that, sometimes solution will take much time to run, or sometime it may diverge also. So if it is a coarse mesh, you can enable these 4. Then simply from the inlet, I will initiate. Then I will run. I have taken some around 17,000 cells here. So it may converge in around 2,000. Sometime worst case 3,000 iteration it will be converged. So I have taken 2,000. Okay, so in my case it converged with 1,000 iteration, and the result, if you see, by default there will be a velocity magnitude, and if you display this, how I am getting the shock, that is exhaust jet, as I mentioned, it is diverged, so I am getting the expansion fan. Instead, if it is a contoured nozzle with the wall aligned with the horizontal axis, I would get without any this expansion fan. Okay, that is an issue here. So you can check the velocity, you can check the Mach number. See this how Mach number varied. You can check the density, like that. Many parameters you can check here. So this for the first case. Then for the second case, like over expanded, what I have to do? No need to change anything. Only in the boundary condition, this outlet pressure, I will increase the pressure. For example, I am giving some 0, that is 20,000 I am adding. Previously 2,000, I am increasing the back pressure to 20,000, so that you will see the variation nicely. So just you have to add. Then I will just once again ensure the reference conditions. It is from the inlet only, and reference zone is empty. Then I will initialize from the inlet, initialize, then run. Let's see how it is coming. So around 3,332 iteration, the solution got converged. So we'll go to the contour. Again, by default, velocity magnitude we will check. So this is for the over expanded. We have given the very high pressure at the exit. So there is a over expanded at the oblique shock wave. So this is the velocity contour. You can check the Mach number contour. If you want additionally, you can check the density. And the density, there are Slayer option. So for example, if you use this rescaled stream wave Slayer, you can see the shock cells like that. So different contour you can create it. So this is the over expanded nozzle with the oblique shock. Okay. Now you will go for the under expanded. I will give some very low pressure so that we can go for the highly underexpanded case, highly divergent case we can see. So again, for that, just in the boundary condition, pressure outlet, I will change this value. This time maybe I will give some 258. Okay, very low pressure I will give. Apply. Then in the reference value, I will ensure if it is from inlet and there is no zone selected for the reference. Then initialize. Then run calculation. For example, for 2000 first I will run. So here solution converged at 974 iteration itself. So here if you check the contour, first I will check the velocity contour. So fit to window. So this is the underexpanded with the expansion fan created. So I have given very minimum pressure. So there is a huge large diverged flow we got it. Okay, as I defined the very low pressure at the back side. So this is the Mach number contour for the under expansion with expansion fan. That's it. Like that, by changing the back pressure we can find perfectly expanded, over expanded, under expanded nozzles. And this, if you double click on this color map, see here you can change. By default it will be exponential. You can change that to float. By default 2 precision will be there. If you want you can keep, otherwise you can reduce the precision. Like that, this color map you can adjust, and this position also you can adjust. You can little bit increase the size. Those things you can do it. Okay, you can fit to the screen. Then you can go for the saving the image. So file, save picture, JPG with a white background. Like that you can save the final output file. Yeah, that's it.